Hello, I will be discussing TRITON Systems Phase 2 STTR results entitled Low Thermal Conductivity Composite Skin Materials. TRITON Systems is a small business located in Chelmsford, Massachusetts, about 30 miles northwest of Boston. TRITON was established in 1992 based on advanced materials development. During the past 30 years, TRITON has diversified into a multidisciplinary company with over 100 scientists and engineers developing technologies for the government and commercial markets. TRITON leverages SBIR seed funding to develop technologies that can then be brought to market either directly by TRITON or through the creation of a spin-off company. In the last 15 years, TRITON has generated over $4 billion in shareholder value through its spin-offs and received the 2017 Tibbets Award for these efforts. Recent technology transition successes for DoD include advanced materials products that have been implemented on premier military aerospace platforms, including a specialty class of materials whose life cycle cost savings impact alone is over $550 million on a single platform, and adhesive products for several aerospace platforms providing performance improvements and helping enhance aircraft availability. The Navy challenge, for which this technology is being developed, is urgent, and the requirements are very well defined and platform specific. There is also strong interest and collaboration from the platform. This enhances the chances of successful transition if the technical effort is successful. It has been found that during certain maneuvers, the engine exhaust of one rotary-winged vehicle may impinge on the side of the aircraft for up to 15 minutes. The recorded temperature is on the order of 500 degrees Fahrenheit, thus exceeding the tolerance limits of the composite skin of the craft. Typically, the adhesive bonding the skins and core of a sandwich composite have significant degradation of its properties when subjected to temperatures exceeding 300 degrees Fahrenheit. The technology developed by TRITON was initiated by a Navy need to develop a lightweight heat shield to protect the carbon fiber reinforced sandwich composite aircraft skins from engine exhaust impingement. The heat shield was designed to prevent the composite's adhesive from reaching 250 degrees Fahrenheit at equilibrium when exposed to the 500 degrees Fahrenheit exhaust. Further, the heat shield must be able to withstand the accidental impact of tools being dropped on it, about 8 foot-pounds of force, with minimal damage, be resistant to water and sand erosion, survive humidity, chemical, salt fog, and thermal shock exposure as prescribed by MIL standard 810H, and endure vibratory loading induced by the rotorcraft. Currently, the rotorcraft utilizes a metal plate bolted to the aircraft side to act as the heat shield. The plate is separated from the aircraft skin through an air gap of approximately 1/4 inch using non-conductive spacers, as seen in the figure in the lower left. As shown, TRITON's composite hybrid solution in the lower right is a composite insulator also bolted to the aircraft side with a similar volume profile as the metallic approach. TRITON's heat shield has been shown to reduce the thermal load on the aircraft skin and be 40% lighter than the current metal solution. TRITON's heat shield has been shown to be considerably lighter, 40% as just mentioned, than the metallic shield, with up to a 20% improvement in reduction of the thermal load to the underlying carbon fiber reinforced polymer sandwich composite structure. TRITON's heat shield has been scaled up to the 2 foot by 2 foot level for use in thermal performance testing. As seen in the pictures, when the front of the heat shield is exposed to about 500 degrees Fahrenheit for 6 hours, The back of the carbon fiber reinforced sandwich composite is still at about 160 degrees Fahrenheit. Samples of the heat shield were also tested and passed for impact, blowing sand erosion resistance, and rainwater erosion resistance. In order to increase the manufacturing readiness level of the heat shield, a 3-foot by 1-foot curved panel has also been fabricated. The current development phase of the STTR effort is a Phase 2 option, which began in July of 2021. In this phase, we plan to complete the long-endurance chemical and salt spray exposure testing and fabrication of a full-scale, about 32 square foot, doubly curved heat shield prototype. This full-scale prototype will undergo platform-appropriate vibration survivability testing. A manufacturing plan, cost analysis, and supply chain will also be developed during this effort. Additional prototypes will be fabricated to allow flight test verification during a follow-on effort. As noted, the heat shield must be able to reduce the temperature seen by the aircraft's composite skin's adhesive to below 250 degrees Fahrenheit when exposed to the hot engine exhaust at 500 degrees Fahrenheit. Further, it must meet the mechanical and chemical resistance requirements to pass mechanical impact, blowing sand and rain erosion resistance, and exposure to a variety of common chemicals and solvents utilized around the aircraft. The heat shield can provide significant maintenance and logistical cost savings compared to repair and replacement of the aircraft's composite skin. Further, TRITON's heat shield has 40% less weight than the current metallic shield, thus saving weight for the platform. To facilitate transition, the TRITON heat shield is being developed to be a drop-in replacement as a retrofit for current vehicles as well as for new builds. In order to transition the technology to the fleet, there are still multiple tests that need to be performed. As previously noted, the current effort is a Phase 2 option. In this effort, we are working on increasing the technology readiness level through further testing of the environmental exposure survivability for this technology. As listed, we plan to perform chemical, thermal, salt spray, and vibration exposure testing of the heat shield during the current effort to demonstrate its ability to meet the platform's requirements. Further, we will be increasing the manufacturing readiness level as we work towards building full-scale prototypes and refining the manufacturing plans. For example, establishing exact manufacturing processes, process control documentation, quality control, and a robust supply chain for the materials for this product. We have a strong focus on transitioning this product to the current identified platform. Throughout our technology development, we have been working closely with the rotorcraft prime contractor and NAVAIR to a very specific set of requirements. With their help, we have also defined the specific tests and the required test data to be collected in this phase that can provide the confidence to progress to actual vehicle flight testing on the current platform during the next phase. In addition, given the wide potential applicability of this technology and product, we want to connect to other platforms that have similar thermal control needs. Thermal control, both hot and cold, is important for many vehicles. TRITON's technology is a potential solution for vehicles where a durable, lightweight shield is desired. Our fabrication methods for the heat shield allow great flexibility in designing and producing heat shields to specific platform requirements. We look forward to helping apply this technology to your needs. If you have any questions or like further information about the heat shield or TRITON Systems' other technology developments, please visit our table at the Navy STP booth or feel free to contact us. Thank you for your attention.